Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to describe how gravitational potential energy terms are calculated and why they're calculated the way they are. So we're going to imagine we got Timmy back here standing on the edge of some building, and again in this discussion we're going to focus mainly on the ball, not on Timmy himself. So imagine Timmy drops this ball from an initial height that I'm calling y1 as measured by a coordinate system on the ground here. So this is supposed to be an x, y coordinate system. And we're just going to kind of take a look at what happens as the ball accelerates down to this second position here that I'm going to call y2. And what we're going to do is talk about how the potential energy terms are actually derived. So potential energy terms are derived from the following concept here, that the change in the potential energy of any system is equal to the opposite of the work done by the conservative force. First question that probably comes up is, well, what do you mean by conservative force? Well, I'm not going to go into that in this video here. The intention of this video is to just talk about how the potential energy terms are calculated. I've got other videos on conservative forces that I would suggest that you go look at. So for now, we're going to look at the work done on that ball as it accelerates from 1 to 2. And I'm going to start with a free body diagram. And you got to imagine the free body at kind of a middle location. So here's my picture of the ball. The only relevant force here is the gravitational force down, equal to mg. Even if we wanted to include air drag, it is still not important for what we're trying to do here. If we were trying to find the net acceleration of the ball, air drag might be an important force. But since we're only trying to calculate the work done by the conservative force, which is in this case the gravitational force, it doesn't matter if we consider air drag acting on it or not. Now remember, work is force times distance. The force is equal to mg. The distance is the distance between the two positions. That's from here to here in this picture. That distance would equal y1 minus y2. All right, I'm going to get that distance by taking the total distance y1 and subtracting the final distance here. Now the work term, the work done by gravity, would be a positive value. Remember the plus and minus signs on work terms. When the force, which is this vector, is in the direction of motion and the ball is falling down, then the work is considered positive. So the work done by gravity would equal this expression, which is a positive value. The change in potential energy for our system is equal to the opposite of the work done by the conservative force. So that would actually equal minus mg times y1 minus y2. It's pretty easy to show by the time you distribute this minus sign that what we're looking at is mg y2 minus mg y1. So this expression represents the change in potential energy of the system. Now remember, change in anything is final minus initial. So this term right here is our final potential energy. This term is our initial potential energy in this case. So this term, mg times y, represents the potential energy at any given y value. So gravitational potential energies generally look like this: mgy, where y is the height measured from some coordinate system. Or if you look at some books, actually most physics books will probably write this out mgh, where h is the height of the object with respect to some measured coordinate system. Now, potential energy terms are position dependent, right? You can either call the height y or h, it doesn't matter. And important thing to realize is that this, the y coordinate, depends on where you put your coordinate system. You can put your coordinate system anywhere you want. In this example, I've put the coordinate system on the ground, and that means that this value, the y value or the h value, however you want to think of it, is 0 when the ball is at the ground. In fact, it's 0 as long as the ball is anywhere along this horizontal line. That means that the potential energy of the ball is 0 on this line. This line has a very special name. It's called a datum. anytime you deal with potential energies, one of the first things you typically do is define a datum. The datum is the, well, I said line, but really it's an area because it kind of comes at you and goes away as well, where the potential energy is 0. Where you put your datum is really completely irrelevant in the problem. In the example that I have shown, the ball's potential energy will be 0 whenever it's on the ground. Up above the ground, maybe up here, we would say the ball has a positive potential energy. If the ball were somehow below ground, the potential energy would be some negative number. Might be thinking, how can that happen? Well, maybe somebody dug a hole here so that the ball could fall all the way down to this location. So up in this region, the ball's potential energy would be considered positive. At about this location, its potential energy would be 0. Down here, its potential energy would be some negative number. Now, it turns out where you put the datum never matters. The only thing that ever matters in any problems are differences in potential energy. So you could very easily put a datum here if you wished. If you did, the potential energy at this location would be 0. The potential energy here would be some negative number, and down here it would be some relatively large negative number, like larger in a negative sense. Like if the potential energy here was something like -10, then the potential energy here would be like -13 or something like that. If we put the datum in the middle, at this location the ball would have a positive potential energy. At this location it would have a 0 potential energy. At this location it would have a negative potential energy, and so forth. So it never matters where you put the datum. The only thing that matters is differences in potential energy anyway, and you'll see lots of examples in my upcoming videos about why that is. So for right here, right now, potential energy is energy due to position. One of the first common types of potential energy that people get introduced to in physics is gravitational potential energy, where the gravitational field is constant, meaning that this is only true as long as we're reasonably close to the surface of the Earth. You know, we're not talking about on a planetary type scale. And this is how gravitational potential energies are calculated, mgy, where y is the height or the y coordinate above some datum. Or you could say mgh, either one. Hope this video helps. Have a great day.